All right, good afternoon. Let's do a synthetic problem to start off with for a warm-up. It's right here. So you're supposed to start with this material here and convert it to this compound over here. And on first sight, that looks pretty intractable. And so the first thing to do is first analyze the problem to see what's there, whether there are any patterns that you can recognize, anything useful. And you can see that for starters, you've got two 6-membered rings here. This is a 12-carbon compound. The product has much less. It's a 9-carbon compound. There are two things that are similar, namely there's a 6-membered ring in the starting material, which I suspect would be useful to employ in the formation of the product. In other words, this 6-membered ring has to come from the starting material somehow. Okay? Then we have an isopropyl group that's hanging off here, and somehow this has to be introduced. So at this stage, it's worthwhile using the principles of retrosynthetic analysis, working backwards from the product. You can also, in a way, once you've recognized that indeed all you need is 6 carbons from this compound, not 12, you can perhaps think of ways in which you can cleave this into a 6-carbon compound for which there's an obvious reaction. So let's first start working backwards. So retrosynthetically, this is a hydrocarbon. It's got no functions in it. So this is totally useless as such. We need to put in functions. So the functions that you can put in retrosynthetically are the ones that you can then remove in a forward step. And we've discussed some of those in the past. Primarily multiple bonds like CC double bonds, CC triple bonds, because you can hydrogenate them off. Halides is a possibility because you can turn them into a Grignard and then hydrolyze that off. Or carbonyls, because we have various ways of removing a carbonyl. So bearing in mind that you have to introduce a substituent conveniently, there are various solutions to this. But within the context of what we've been discussing, I'm going to use a carbonyl because we know how to alkylate carbonyl compounds. So I'm going to just put in a carbonyl, and the place to put it in, I mean, you can put it in any way you want, but the place to put it in is next to the group that you want to introduce. So I'm going to put it in here. And now this becomes already a little clearer, right? Because you know that by enolate alkylation, you can put in a substituent next to the carbonyl function. At the same time, and so one can work further backwards and say, okay, this has to be derived from a cyclohexanol. Now that you have a 6-membered ring that is much simpler and is functionalized, you can also look at the starting material and try to solve the problem of how to turn this 12-carbon compound into a 6-carbon compound. And it's obvious because the way you have to cleave is here. So in a forward sense, you know that by ozonolysis, this can be turned into cyclohexanol. Ozonolysis meaning ozonation followed by reduction. It's a 2-step but 1-pot procedure. So typically it's written over an arrow as 1,2 because you don't isolate the intermediates, the ozonide intermediates in this reaction. And if you stare at this and then stare at this, there's the obvious, you've got the problem solved. At least topologically with the gross outlines of your retrosynthetic analysis. So now the task is to do the nitty-gritty of working this forward. And so retrosynthetic analysis doesn't completely provide you with a solution because now you have to worry about details of your synthetic scheme, okay? Reaction conditions and the like, and whether the reactions you had envisaged actually will work the way you had envisaged them. So in the forward sense, the synthetic scheme, that is the solution to the problem, would be first step is ozonation followed by reduction, and you can use dimethyl sulfide or zinc acid reduction, and that gives you cyclohexanol. And at this stage, looking at your retrosynthetic analysis, you may think, okay, I'm almost home because all I have to make is make the enolate with LDA, and then I dump in the alkylating agent. Trouble is that the alkylating agent would be a branched iodide or bromide, a branched system with steric hindrance. And remember, there's a big limitation on enolate alkylations, namely they're strong bases. And absolutely, with a secondary haloalkane that would introduce an isopropyl, this would give you elimination. That step just wouldn't work. Okay? So we have to think about some solution to that problem, and that was what we discussed last Tuesday, namely enamine chemistry. Okay? That solves the problem because enamines are neutral enolate anion equivalents. They can be alkylated, and they don't do eliminations with secondary haloalkanes. So what we have to do is convert this first into the enamine, and you can use any secondary amine you want. This one is convenient. That's most often used, but you can use dimethylamine if you want, or related secondary amines. And that will give you the enamine. And now we have a species where this beta carbon is nucleophilic, okay? And so we can just treat that with 2-bromopropane, and then work it up with acidic water, which is the step that will cleave the iminoamine that you get after alkylating here. So the electron pair goes in here, this goes out, alkylates, does the SN2, and then you get the iminoamine that then is hydrolyzed by the normal imine hydrolysis mechanism to the corresponding cyclohexanol. And now we're almost there. To connect this to product, we need to remove the carbonyl. Okay? And that we can do most conveniently by Wolff-Kishner reduction, hydrazine, sodium hydroxide, delta. Okay. And that's it. Yeah?
What about instead of like alkylating, what if you get like an alkyl condensation and then hydrogenated it with like acetone?
Okay, so the question is really related, are there other solutions to this? And you wanted to do over here, an aldol condensation with what? Acetone. Yeah. And yeah, that would introduce a 3-carbon piece, and then by some, actually you can do the condensation and then hydrogenate off the double bond. Perfect solution. So the answer, in general terms, there are several solutions to this problem. So as a piece of homework, think about several other ones. Okay? Because you can, not only from here can you get to the product in other ways, but you can also, in your retrosynthetic analysis, the first step, introducing this carbonyl function, you can think of solutions where you put in a double bond at a strategic place, okay? Which is perfectly okay to do. And this morning there was another one, somebody came up with a Wittig approach, similar to yours, and then hydrogenation. So there are several solutions to this, and in the exam, there will be several solutions to the problem. Some of them we may not even recognize that they're possible. but you will fight them, and you'll get full credit. Okay? That's part of the fun of grading some of these exams. At this stage, you're building up sufficient synthetic repertoire that there's several possibilities that you can explore. Okay, so we were going along the stuff that's shown on the slide. We started chapter 17 with additions to the carbonyl function, and remember, there were several nucleophiles that we used, and the mechanisms are all the same. Typically, or frequently, acid or base catalyzed. If it's acid catalyzed, mechanistically, you first protonate on oxygen, then you come in with a nucleophile. If it's base catalyzed, the nucleophile attacks first, often nucleophile as a negatively charged species, like hydroxide, and then you protonate second. Okay? And we did this for HCN, so cyanide. We did this for water, to give hydrates. We did this for alcohols, to give hemiacetals. And we did this for alcohols to go all the way to acetals. We did it for carbon-based nucleophiles other than nitrile, namely the aldol reaction, okay, where an enolate attacked here. And that's, I think, where we stopped last Tuesday. The aldol gives rise to alpha-beta unsaturated carbonyl compounds, and we recognize that these compounds are functionally like extended carbonyls. Okay? Just like a single double bond is related to butadiene, a normal aldehyde ketone is related to an alpha-beta unsaturated ketone. And because of resonance, the delta plus, or the full plus, if you write the fully dipolar structure here, which has a minus here and a plus here, is an allylic cation. And allylic cations, you remember from the beginning of the semester, both sides can be attacked by nucleophiles. And indeed, they do. And so nucleophiles will attack both here and here. Now, attack here with all the nucleophiles that we've been discussing, that I just summarized for the attack here. Remember that? Those were reversible reactions. Okay? In some cases, the equilibrium lay to the left. In the cases where we isolated compounds like the aldol reaction and so forth, they either lie to the right or they're driven by a subsequent step. In the aldol addition reaction, it's the dehydration that drives it all the way to the right. But otherwise, they're reversible, okay? And even regardless of where the equilibrium lies, even if it's exothermic, the exothermicity doesn't prevent the reaction to be still in equilibrium with starting material, okay? So that the equilibria are reachable. So in this case of the alpha-beta unsaturated carbonyl, kinetically, the nucleophile will still attack here because there's more plus here than there's here, okay? And the reason for that is the inductive power of oxygen on the directly neighboring carbon, which tapers off quite a bit with distance. Okay? Resonance-wise, they're equivalent, but inductively, the oxygen pulls here much more than here. And that's in part the reason why there's more blue here than there is here. So kinetically, we'll hit here, but it's reversible, and every now and then it will hit here. And the attack at the beta carbon, the conjugate addition, as it's called, is thermodynamically favored, okay? Because you're in the final product, the carbonyl group is preserved. Okay? This concept of vinylogous carbonyls, you can keep on going, okay? Just like from butadiene to hexatriene to octatetraene, it's related to conjugated pi systems where the two ends know of each other. They communicate through the pi frame, like a molecular wire. Okay? And so adding another double bond, you do the same kind of chemistry. Nucleophilic addition will be preferred at the end because the product in the end is actually a substituted alpha-beta unsaturated carbonyl. Okay? And et cetera, you can go on forever. Well, it hasn't been done for a really large system, but it's been done for, as far as I remember now, up to 5 double bonds. And the record, I think, was 5 double bonds, but it may be even larger now, to show that the principle works. In part, this hasn't been explored ad infinitum because once you get to really large poly-enones, they actually become unstable or too reactive. They become air sensitive, a little radical. Anything that is reactive in any sense will attack polyenes because the resulting species are all stabilized by resonance themselves. Okay, so it's easy to mutilate a conjugated polyene bond. So at the very end of last Tuesday, we did the first example of this, namely cyanide addition, and that's still up there. So HCN adds, and it adds to the beta carbon. And again, just to rub this in, this makes HCN, and the cyanide attacks here faster, but it's reversible, and every now and then it attacks here, and that's a thermodynamic product because the carbonyl is retained. And this addition, this mode of addition, is called 1,4 addition, and that's a colloquial term because you count the reactive unit as 1, 2, 3, 4. It's 4 atoms. So the addition occurs at the termini. Okay? And addition to the carbonyl is called 1,2 addition. Okay? So can we continue as we did for the simple carbonyl compounds? And the answer is yes. It's actually completely trivial now. You just do everything we did on aldehydes and ketones with respect to nucleophiles. You do it for alpha-beta unsaturated carbonyls. So for example, water or alcohols will add by so-called conjugate addition. So with water it's hydration, with alcohols it's ether formation, meaning attack at the beta carbon. So this enone here, 3-butenone with basic water, let's go at -5 degrees, hydroxide adds at the beta carbon. And out comes this. Notice that this water attack, when we did this on aldehydes and ketones, made hydrates. And hydrates, that's where we started discussing this whole game of equilibria, right? And we said that reactive carbonyls, the equilibrium is to the right. For aldehydes, the equilibrium is about 1, it's about 50-50. And for ketones, because the carbonyl function is slightly stabilized, it's to the left. This is nothing else but a vinylogous hydration, if you wish. And notice that now, because we're retaining the carbonyl function, and we're formally, topologically adding HOH across a simple CC double bond, that's the end outcome of this transformation, that the reaction now is exothermic. And so this equilibrium arrow now I'm writing purposely to the right. You may recall that hydrations of alkenes are exothermic. That was the Markovnikov hydration, chapter 12. Acidic water as HOH to make alcohols. And there is a table at the very beginning of chapter 12 that gives you roughly estimated delta H's for these reactions. And for water, I think it was -7 or 8 or something like that. A few kilocalories to the right. This reaction in a carbonyl hydration, remember, was endothermic. Okay? Because you're destroying the carbonyl function. So remember, mechanistically, hydroxide attacks in a conjugate fashion, so you push arrows to give the enolate. The enolate, when it is trapped by a proton, remember, kinetically, always first hits the oxygen to make the enol. But the enol then, through the enol-keto tautomerization, namely deprotonation on oxygen, so this is a reversible step, eventual protonation at this carbon of the enolate gives you the final product. Okay? So if you write a mechanism, you have to be cognizant of this, even though in the end, this looks like a Markovnikov hydration, even though the mechanism is different. So this is hydration. So what about nitrogen nucleophiles? Amine additions. Same thing. We take an amine, it adds to the beta carbon, and out comes the aminated double bond. So we're essentially adding the elements of NH across the CC double bond with the beta carbon bearing the amine. This also is an equilibrium that lies to the right, clearly to the right, and you can isolate all these compounds in good yields. You can do an intramolecular version of this for amines. You can also do it for alcohols. If this were OH, you would get a cyclic ether. For the amine, you get a cyclic amine. And here again, it's beta attack, and then the enolate that's formed is protonated, because of the ring fusion, the product of this cyclization is preferred to be cis. Okay, so thermodynamically, cis is more stable than trans. That's just an aside. Without this bridge, trans would be more stable than cis. But because of the bridge, to link a trans fusion is now more sterically incumbent than to link a cis fusion. So what about carbon-carbon bond formation? Organometallics. Well, we sort of already know what happens with the ones that we know. Alkyl lithiums and Grignard reagents add mainly 1,2. Okay, so here I'm repeating an example from earlier. Methyl lithium on this guy will add to the carbonyl and stay there. Why is this the case? Well, remember, the first addition of these nucleophiles typically is always on the carbonyl because there was more blue on this carbon. And the only reason we are seeing conjugate additions with cyanide and water and amines and the like is because that step is reversible. Well, with alkyl lithiums and Grignards, it's not. So you're getting a kinetic product. It just adds, and you get the alkoxide, and that doesn't come back. Okay? Because taking an O- and come back with the electron pair and kicking out, in this case, methyl, is a no-go. That would mean that methyl anion would be a leaving group, and that, absolutely doesn't want to do that. So you're stuck. And that's what you get. Good deal. So this was for a long time a major problem that organic chemists tried to solve. And then they started discovering the rest of the periodic table. And organic chemists started exploring organometallic compounds in a more general sense using all kinds of metals. And during this exploration, they found that a variant of an alkyl lithium, namely a so-called cuprate, does exactly that. So cuprates you get by taking 2 moles of alkyl lithium and copper iodide. That's the stoichiometry for your use. It's just alkyl lithium plus copper 1. And out comes a dialkyl copper lithium reagent. In this case, it's called lithium dimethyl cuprate. It's a mouthful. You don't have to remember that. It's a cuprate would be useful to remember, or copper reagent if you want. But it's dialkyl copper lithium. That is the stoichiometry if you analyze it by elemental analysis. But the structure of these things actually is solvent dependent. They're aggregates. They're sometimes quite complex tetramers and pentamers and hexamers and so on. So we write them to simplify things like this. Okay, simply R2 copper lithium, where R is the R group that's derived from the alkyl lithium. Those reagents, so this is a piece of vocabulary that you have to remember, okay? R2 copper lithium. So if you want to add an R group to the beta carbon, you have to use this, and that works. Okay? And there's an example, this enone here, with dimethyl copper lithium, this can be done at very low temperatures. It adds beta, and then you work it up with acidic water, and out comes the beta methylated compound. And that's a powerful retrosynthetic disconnection if you're thinking about disassembling retrosynthetically a carbonyl compound. If that carbonyl compound has a beta alkyl group, one way to introduce that alkyl group is by this conjugate addition using the dialkyl cuprate reagent. And the reason that this works, by the way, is because the mechanism actually changes. I won't go into the mechanism, but it is an electron transfer mechanism. That is, the anionic reagent actually picks up, donates an electron to the enone to make an enone radical. And that then rapidly collapses, and because of the peculiar features of the orbital coefficients at all the orbitals, that coefficient is rather large here, they'll grab that guy faster. Okay? So it turns around. It's no longer Coulomb's law. No longer plus charge here attracting the negative charge. It's a radical species where the rules change. Okay? And it just so happens to be conducive to attack at the beta carbon. So one of the beauties of this transformation, when you think about it, is that the cuprates, of course, are like Grignard reagents and like alkyl lithiums. They're extremely basic. They're therefore very moisture sensitive, so you have to keep moisture out. The solvents have to be bone dry. They are typically THF, distilled from potassium, okay, to all waters out. And you keep them air free because the reagents are also air sensitive. And you do the reaction. You take your enone and you add the cuprate, and you wait for a few minutes at -78, this guy 4 hours. And then what you get, of course, initially in the pot is the methyl, in this case, or the alkyl in general, having attacked here, having generated an enolate anion. So you're actually in situ, in your pot, by this reaction that makes a carbon-carbon bond, have generated an enolate anion. And so chemists didn't take chemists very long to realize, well, let's use that enolate anion because I can alkylate it. Okay? Again, caveat, it's an enolate anion, very basic, so alkylation is limited. But I can definitely methylate. I can allylate with an allylic halide, and I can use a benzylic halide, halides that are not prone to elimination. And so, indeed, that's what can be done. And so in the general scheme, what this allows you to do is start with an alpha-beta unsaturated carbonyl compound and add 2 different alkyl groups across the CC double bond. That's a spectacular reaction, which you haven't seen up until now. Okay? In terms of ease of procedure and increase of complexity of your products compared to the starting material. And so what happens is, the first step, the cuprate adds to the beta carbon that introduces the red R, and then you get an enolate anion, and if R dash here, the blue R, is chosen appropriately, that alkylation is feasible, then you introduce a second R group. Okay? Here's an example, cyclopentanone with diphenyl copper lithium. So I'm using the phenyl lithium-derived cuprate. And it adds phenyl group to this position here, and then